Have you ever looked up at a massive skyscraper or driven over a long bridge and just wondered, what is that really made of? We all think we know, but the truth is the concrete that holds our entire world together is based on a kind of secret recipe. It's a precise science, and today we're going to decode it. So let's just get one thing straight, right off the bat. If you think making concrete is as simple as, mixing a few basic things in a wheelbarrow, you're missing the most important part of the story. Modern concrete is an incredibly advanced, high-tech material. And that really gets to the core puzzle here, right? The concrete you need for a huge dam is totally different from the concrete you'd pour into a really intricate mold for a piece of art. So how on earth do engineers create these wildly different materials using the same basic components? Well, that's exactly the question we're going to answer. Here's how we're going to break it all down. First, we'll look at why it's so much more than a simple recipe. Then, we'll dive right into the design process and the key ingredients. We'll even put together a real recipe, step by step, before checking out concrete's special powers and, why any of this really matters in the first place. Think of creating the perfect concrete. It's less like casually cooking dinner and a lot more like high-stakes baking. You can't just eyeball it and throw things in. Every single measurement has to be absolutely perfect, and you need a master guide to get it right. Yeah. Every single structure, I'm talking everything from a house's foundation to a nuclear power plant, needs its own unique recipe. And for engineers in India, that master guide, the ultimate cookbook for concrete, is a document called Indian Standard 10262. This is the rulebook that guarantees everything is strong, safe, and built to last. So how does this whole process even start? Well, the very first step in designing concrete isn't about ingredients at all. Nope. It's all about strength. First, you have to figure out how strong the final product needs to be, and then you have to aim even higher. This really important idea is called the target mean strength, and it's crucial. See, because of tiny, unavoidable variations in materials, or the temperature, or the mixing, you just can't aim for the bare minimum strength you need. You have to build in a safety buffer to make absolutely sure you never, ever fall short. The standard actually turns this idea into a pretty simple formula. Step 1, you define your minimum required strength. We'll call it FK. Step 2, you add a safety margin, which is calculated to account for all those real-world variations. And step 3 gives you your target strength, F tilde. That's the higher number you actually design your mix for. And check this out. Here's how that safety margin actually works in practice. This table, taken right from the IS standard, shows the safety buffer for different grades of concrete. Do you see the pattern? As the concrete grade gets higher and stronger, that buffer gets bigger. For something like M65 and above, the stakes are just so much higher and the mix is more sensitive, so you need a much larger margin of safety. Makes sense, right? Okay, so once you have your target strength locked in, it's time to pick your ingredients. This is where the real art and science of proportioning comes in, balancing all the components perfectly to hit that target number. All right, if you remember just one thing from this entire explainer, please make it this. The single most critical factor that determines how strong concrete will be is the water-to-cement ratio. It is the golden rule, period. This graph from the standard shows it perfectly. Just look at the bottom axis. That's your water-cement ratio. As you move to the right, which means you're adding more water, just follow any of those curves up, and you'll see that the strength on the left axis goes down, down, down. It's a direct inverse relationship. Less water gives you a denser, stronger concrete paste. Too much water and it all turns weak. It's exactly like adding way too much milk to cake batter. But of course, it's not just water and cement. You've got this whole supporting cast. You've got coarse aggregates, like gravel. Think of these as the bones, giving it a structural skeleton. Then you have fine aggregate, which is sand. That's the filler that gets into all the gaps. Chemical admixtures are like spices. They let you tweak the properties. And mineral admixtures, like fly ash, are kind of like flour extenders that can improve performance and sometimes make it more environmentally friendly, too. So we have our target strength. We know our ingredients. Now for the fun part. Let's put it all together and see what a real, fully engineered recipe for high-performance concrete actually looks like. Okay, let's build the recipe for 1 cubic meter of a strong M40 concrete. We're going to start with the heart of the mix, the binder. That's 412 kilograms of cement. Next up, that all-important ingredient, water. We need exactly 148 kilograms. This gives us that super precise low water to cement ratio of 0.36, which is absolutely essential for getting high strength. Now for the filler. To fill in all those little gaps between the bigger stones, we're going to add 648 kilograms of fine aggregate, sand. And finally, the skeleton of the mix. This is a massive 1,234 kilograms of coarse aggregate. This is what provides the real bulk and the structural stability. And there you go, that's it. That is the final, precise recipe for 1 cubic meter of M40 grade concrete, calculated right from the guidelines in the IS 10262 standard. That's precision engineering in action. But here's what's really cool. This super meticulous design process isn't just about making standard concrete stronger. It actually unlocks the ability to create super concretes, materials with amazing properties for really specialized jobs. Just take a look at this comparison. On the left, you've got your standard concrete. It's thick, kind of sludgy, and you have to vibrate it to get it to settle. But on the right is self-compacting concrete, or SCC. By just tweaking that recipe, adjusting the aggregates, adding special admixtures, engineers can create a concrete that's so flowable it pours like a thick liquid. It fills the most complicated shapes all by itself. This is the stuff you'd use for that delicate sculpture we were talking about. So, why does a really technical document like IS 2062 matter so much? I mean, why should you care? Because it's about so much more than just a recipe for concrete. It's the blueprint that guarantees safety, that guarantees consistency. It's what allows us to build taller skyscrapers, longer bridges, and infrastructure that can actually stand the test of time. This standard is this quiet but absolutely essential tool that makes our modern world possible. I mean, this level of precision is already leading to incredible innovations, like self-healing concrete, or even concrete that can store carbon dioxide. It just leaves you with this fascinating question. If this is the science behind the building blocks of today, what will the secret recipe for tomorrow's world look like?